hello. 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 Okay. And wait. What do we? Oh, screen turning up. Okay. So I think we are close to finish grading midterm. So today we'll just have the explanation of midterm. So I think people are not doing too great. We are not doing too great on midterm, but we should be able to finish grading this week. And I will explain some of the common mistake in midterm today. So any question about particular thing you want to ask before I go through everything? Okay. So midterm about the first 5 problems are basic. So if you are not getting good grade on them, you should really do more practice yourself. So for example, problem 3 and problem 4 they are very standard. So you need to do Gaussian elimination to find the reduced rotational form, and or you can use it to solve linear systems. Okay. And so I guess people mostly don't know what they should be doing, but people are still making mistakes in their calculations, so just be careful. And these are like the answers to the reduced rotational form. I think only conceptual problem here is a few people are making are confusing reduced rotational form and rotational form. Okay. So reduced rotational form means whenever you have a 1, then the same column must be all others must be zeros. So you need to have 0 here, etc. Okay. So you need to go to reduced rotational form. Okay. And we have time, so maybe let's try. Can I do this here in real time? No. Okay, that thing is very annoying. Let's see if I try to do this. Okay, let's try to do this in real time, I guess. So if I want to make this reduced rotational form, then I will probably pick swap those 2 rows to the top and take a -1, so it'll be easier. So 1, 1, 2, and 3, -2, -2, 3, -2, -1, and -2, -3, -2. And then we eliminate first column, okay? And that will give me 1, 1, 2, and so -3. So okay, so I should have all 0 here, and -3, so it becomes -5, and -3, -6, -8, and 0, -5, and -7, and +2. So it should be -1 and +2. Okay, and then if I swap those 2 again, 1, 1, 2, 0, 1, -2, 0, -5, -7, 0, -5, -8, and then I go 1, 1, 2, 0, 1, -2, and +5. So +5. So all 0 here, and so minus a lot. -70, -80. And and you can see that then you turn this equal to 1, and you eliminate everything, and then you go to this form. Okay. So this one is easy because basically because we have enough rank in columns, and it must go to this identity matrix like things. Okay. Yeah. So anyway, that's a reduced operation form and Gaussian elimination. So this is the basic of the calculation for solving linear system. So if you are still not familiar with Gaussian elimination, please do some practice. And yeah, and then let's go back to first problem and the second problem. So they're kind of similar. They are the true-false problem. Okay. Yeah, and well, I guess a lot of people guessing the first problem with just all true answer. That's not the best strategy, but obviously there are some things false. Okay, so anyway, let's go through the yes and no here one by one. And every homogeneous system is consistent. So homogeneous system is like solving Ax equal to 0, and everything, they are all consistent because you can just pick x equal to 0. So this one is true. Okay. And B is saying that every n by n matrix is non-singular if only if it's R, A, E, F is I. And this is true. This is a theorem 1.5.2 that we proved. Okay. So there are 3 characterizations about non-singular matrix. And one of them is this R, E, F equal to I. And this is also can be seen from the algorithm we do to one of the algorithms that we use to calculate A minus 1. That is, you can do this A and I thing, and then you do the row operation to get I minus 1. Okay. So, so when you can get reduced operation from A to I, then you can get A minus 1 here. Okay. So this proves one way of it. Okay. And then C is actually false. So C says that A equal to A minus 1 and A equal to identity or minus identity. And this is not true because you can get a mixture of this identity and minus identity here. So you think, well, so obviously those two satisfy this thing because I square equal to I and minus I square equal to I. But it requires a bit thinking. Then how about we put the I here and the minus I here in diagonal form? And it's still the inverse of itself, right? So this thing, so in the easiest form is you have 0, 1, 0, 0, minus 1. Then this thing is neither identity or minus identity, but it's square. Then you get 1 square here and minus 1 square here, and it's still square to identity, so A equal to A minus 1. Okay. And D is false. D is kind of dumb. So it says product of two elementary matrix is still an elementary matrix. This is just it's just a small definition thing. So yeah, so basically you take any two elementary matrix and you multiply them and you find out that they are really not elementary matrix. So for example, there is an elementary matrix that changes the sign of a row, right? So this is an elementary matrix. This is the elementary matrix that multiply the first row by 2 is this thing, and the elementary matrix that multiply the second row by 2 is this thing, and you multiply them together is this thing. And so you multiply the first row by 2 and multiply the second row by 2. This is not elementary matrix because in terms of the definition of elementary matrix, you can only do this multiplication on one row at one time. So if you multiply on 2 rows at the same time, it's not elementary. And there are other examples that shows that product of two elementary matrices are not the elementary matrix. Okay. And E and F are basically pretty basic theorems we have about bases. Okay. And so E is saying that we have n vector here that are n vector that are IOI, then they span Rn. Okay. So that's the triangle thing we have, remember? So we say like I think it's 3.4. Then we have if you have an n-dimensional space, then there are three things that you satisfy two, then it's a basis. So you have n vectors, and they span, or your vectors span the whole space, or they are OLI. Okay, OLI. And so we have our definition or basis saying that if you are LI and you span the whole space, then you are a basis. And in that case, you will have n vectors because that's the meaning of the dimension of the space. And we also have that any two of them form a basis. So here we have n vectors, and so we have n vector and a span V, so they are basis. Oh, sorry. We have n vector and a LI, so they are basis, and the basis will span the whole space, so they span Rn. And okay, so this is true. And the next one, we say that okay, so it's similar but not true. Okay, but so we have a funny way to say these things. We are saying we have k vectors, and but the span of all of them is same as span of only k minus one of them. So if we get rid of base k, it still span the whole basis. Okay, and but if the span of only k minus one of them equals the span of all of them, then we know it's not LI, because this means this sk can be written as a linear combination of others. So we have it's not LI, so it's not LI, so it's not a basis. Okay, so this is true. And then finally, we have the question of saying that if A is rho equivalent to B, then A, B have the same column space. And this is obviously not true. So maybe just this thing as an example. So this matrix again, so you have 2, 0, 0, 1. Okay. So yeah, so this is just yeah, something we'll see also again. So this is finding a row space of REF, right? So we have been saying in 3.6 that if we find out REF, then can find a row space in the column space of a matrix. So say A equals this thing, and you go to REF, then you just normalize this 2 to 1, right? So it's REF is 1, 0, 0, 1, and yeah, and so this is A and this is B. And so A is rho equivalent to B, but you can easily see that the column space is different. So A is 2, oh, sorry. There are these back examples. So the column space actually is in here. So let's see. Let me get a better example. Okay. Better example should be, so I should actually do row operation. Okay, so A equal to okay, so I think this is better. Or actually I didn't say A is okay, so I don't even say B is REF of A. Okay, so this is even easier. Okay, so A is just what representing, so A equal to this 2 by 1 matrix 1, 1. And I can get rho equivalent B, that's just you do Zora operation, right? So I still get a REF of this thing. So I subtract the second row from the first row. Okay, so B is 1, 0. Okay, and obviously the column space are different, so because the column space of A is spanned by 1, 0, and the column space of B is spanned by column space of A is spanned by 1, 1. And the column space of B is spanned by 1, 0. Okay. And yeah, so row operation give you equivalent row space. Okay, so row base space of both A and B is every real line, everything R1. Okay. So every real number, and but A and B have different column space. And but what we say is that if you look at the pivotal of B, then you can find the basis of column space of A. So pivotal B is here, and then A is spanned by this one vector here. Okay, So any question about problem 1? Is it's a basic question, basic from the books. Yeah. And problem 2, we are asking true-false problem on determinant. And yeah, so A and C are kind of similar, and you have a whole bunch of different order and orientation, but actually they will be all the same. Because here we just need to remember 2 things. So delta AB equal to delta A delta B. Okay. Okay. So from A you need to remember this thing. So because of this, then you have the delta ABC equal to delta A, delta B, delta C. Okay, and so now we have 3 scalar multiplying each other, then ordering doesn't matter, and so that will be. So you can swap those 2 and turn it back to delta, and it's just equal to delta B CBA. Okay. So yeah, so delta and the ordering in the middle doesn't matter because you can decompose them into the product of individual determinants. Okay, so that's A. And C is similar than C. The extra thing you need to know and remember is delta A equal to delta A dagger. Sorry, delta A transpose. Okay. So yeah, so once again, these things is so this delta AB transpose. So use the first thing we have up here. This is equal to delta A, delta B transpose, and as we said, delta something transpose is just delta something, so it's equal to delta A, delta B. And yeah, so that's just equal to delta A transpose B. So A and C are just using these 2 relationships. Okay. Okay. So this thing and this thing, then you can prove that A and B are A and C are true. And what about the middle one? Middle one is actually false. So delta looks very linear, but it's actually not that is because you think about so because this is actually alpha to the dimension. Okay. So if what is it? So A equal to 1, 0, 0, 1, then delta A equal to 1, then alpha A equal to alpha 0, 0, alpha. So delta alpha A equal to delta alpha A will equal to this alpha times alpha, and that's alpha squared instead of alpha of delta A, delta determinant A. Okay. Okay. So that's problem 2. Any question? Not. Okay. And yeah, so problem 3, that's how the calculation. Do we have time? No, we don't actually have that much time. Okay. Yeah, so problem 3, hopefully, if you cannot get if you don't know how to, I think people mostly know how to do calculation, but I guess you just need to be a little more careful when you do calculation. Problem 3 and problem 4. Okay, and problem 5, calculate determinant. So you can do brute force calculation, and it will be not too hard. It's like 6 turns together, but actually we have set up the equation easily. So actually you can do them all very fast. That's because you can say you look up this row and this row, and you see this row is twice over the first row. Okay, and we're saying that okay, and yeah, we have been saying that when you do determinant, you can do row operation, and so this adding a row to another row operation doesn't change anything. So you can subtract twice over the first row here and turn this equal to 0, 0, 0. And so that means that determinant is 0 here. Okay? And the second one is 2 by 2, so you can just do calculation. So this is 7 minus 6 equal to 1. Okay? So this is calculation. And the third one, you also have some symmetry here, so you can do similar thing. So you can subtract the first row from the second row and the third row, and then we get the determinant of this thing 1 1 1 and 0 1 0 and 0 0 3. And so this is a triangular matrix, so you know the determinant is just this thing multiplying together, so it's 1 1 3 and equal to 3. Okay, so this one is a phase calculation. Okay, and so the first 5 quadrants are basic quadrants. Then the 6th one, okay, so the 6th one is a little harder, but it's a thing we told just before the midterm. I don't know, so I guess we didn't practice, but so people are a little unfamiliar with this, but anyway, it's actually very little calculation if you know what you are doing here, okay, and so this is thing that we told in 3.6 at the very end of the section, and we are saying we can find all 3 of those things by actually just finding the REF of A. Okay, so we want to find the REF of A. Okay, so the reducible echelon form. Okay, so once again we find reducible echelon form, and here we have nice numbers. So let's do the calculation here once again. So you want to turn the first column into all zeros. So you subtract the first row from the second row. So then it is 1 minus 1 equals 0. Then 5 minus 4. Did I do the calculation wrong? Wait. Why do I got minus 1? Okay, I think I actually got calculation wrong, but it doesn't matter. Yeah, so you subtract 5 from 4 and it should be plus 1, and you subtract 1 from you subtract 0 from 0, minus 1 from 0, and so actually plus 1, so it's plus 1 here. Okay, so it should be plus 1 here already. 1 1, and yeah, and I can skip this one. Okay, and yeah, so this we have a nice number. So 1 4 minus 1, and 0 1 1 and 0 3 3. Then you subtract this 1 1 from 3 3 once again, so you got 0 0 0 here. Okay. So this is another 4-rank matrix. You only have rank 2. You see, because you have the extra 0 row here. Okay, and okay, so this is REF. Wait, sorry. I subtract here, and okay, so I should need this thing. So this is only REF. Sorry, 0 1 1 and 0 0 0. Okay, so here you already see a rank. So I should label here. So up to here we have. So this is REF here, and we want REF. Actually, we don't need them for the first 3 things, but not for the first 2 things, but it's nice, so it's useful later. So let's do REF. Okay. So and so to get REF, and okay, do I got this wrong? Okay, I got this very wrong at the start. Let's see. And okay, so to get this back, I want to then, so to get the REF, then I want to turn this 4 equals 0. So I have a minus 4 up here. Okay, so this 4 becomes 0, and they become minus 5. Okay, let me cheat a little. Let me check this is correct. Okay, and yeah, I guess so. There are multiple bases for row space and column space, but okay, let's stick to the one we talked in class. That is, okay, so you find the REF, then so okay, so we find the REF here, and so from here we can solve for everything. Okay, so first one is you want to find the basis for row space, And we remember that when we do those row operation, we didn't change the row space. So everything here has the same row space. So you can either say those two things is the basis for the row space, or you can say those two things is the basis for row space. Okay. So yeah. So it depends on the notation, but so I guess to get a better notation, we will say the row space is spanned by those things. So we have a 2-row vector. Okay, that's the basis for row space, and the basis for column space. Okay, so that's a little related to the first problem. It's a problem here. Okay, so once again, remember those columns are not basis for column space, but what we do is we find the pivot here. Okay, so pivot here 1 and 1, and we map to the and we look back to the original columns of A. Okay, so we know those two columns are a basis for the column space of A. Okay, so 1, 1, 0 and 4, 5, 3. Okay. And then we want to find the null space of A. Then here we can we don't have much space, but anyway. And okay, let's see if I can fit this in. Okay, so we want to find the null space of A, and I think what we do is, so A is equal to 0 is same as REF of X equal to 0, right? So we have 1, 0, minus 5, and 0, 1, 1, and 0, 0, 0 of x1, x2, x3 equal to 0. And so you see 3 is a free vector. So that means we can have x1 equal to 5x3 and x2 equal to minus 1x3. And so the null space is spanned by, so it's 5 minus 1, 1 times alpha times x3, right? And so null space is one-dimensional as as our rank nullity theorem says. So rank is 2 and null is 1. Yeah. Okay, so that's the basis for null space. And the last one where should go? Okay, I guess let's go to the blank page because we don't have much space here. Okay, and okay, so maybe here. Okay, so we want AT x equal to b consistent. Okay, I think people are doing this brute forcely. Like you just take AT and solve for things and solve for AT equal to b and try to see when it is consistent. But actually, there is a way to do not much extra calculation by knowing the REF of A, because we know AT is equal to B is consistent, then we have a B in column space of AT, and this is equal to the row space of A, and equal to span of, okay, so now the first thing, and this is why having REF is better, although having REF here already help us solve C, and you can also help them solve P, and it's basically same as the C thing. So we'll see soon. Okay, so it's in a span of I guess here we are doing we are confusing a row vector with column vector, so it's a little confusing. So it's like a row space transpose. So anyway, so that's those two vector transpose is in a span of 1, 0, minus 5 and 0, 1, what's that? 0, 1, 1. Okay, those two column vector. Okay, and yeah, and then we say this thing equal to B1, B2, B3. Okay, and so obviously that means this is equal to, because we have the 1, 0 here and the 0, 1 here. So if you want some alpha, beta, alpha of 1, 0 times 5 plus beta of 0, 1, 1 equal to B1, B2, 3, then obviously this is equal to B1 and this is equal to B2. So this should be equal to B1, B2 minus 5 B1 plus 1 B2. Okay, so you see that B3 is minus 5 B1 plus B2. Okay? Any question about this? Yeah. So yeah, so you can do everything from this REF. Okay, and okay, so let's keep going. We have 10 minutes. Oh, we're actually a little slower. But anyway, okay, so now let's go to the actual hard problem. So those two basically you might or might not be able to do because they are pretty hard problem. Okay. So problem 7 is testing you on how you can do abstract algebra. And okay, so a lot of people try different things, but a good way to see where your problem is. So a lot of people try to say like basically say this thing once again. So they want to say, so anyway, that's not a repeat wrong answer. But a good way to see whether your answer is wrong is whether you have used this. Okay. So yeah, so people have the idea that alpha x equals 0, then alpha must equal 0, but that's not true, right? Because if x equals 0, if x equals 0, then for alpha x equals 0. So this is not unique. And so for example, maybe yeah, so for example, people like if you say alpha plus 1 x tilde equal to x, and then you want to argue that this equal to 1, and this is not true when x equals 0, then this is not necessarily equal to 1, right? Because this can be everything times 0 still equal to 0. Okay. And yeah, so you must use this thing to prove this alpha x equals 0, then alpha equals 0. And so I guess the intuitive way to see this is we are basically trying to prove. So you can think about in a very special case, so like if x is in R1, right? Then we just have so you just have two numbers, alpha x equal to 0 and x not equal to 0. So so if two numbers times multiply each other to 0, then you have either alpha equal to 0 or x equal to 0. Okay. And that, so this is a generalization of this thing to many dimensions. Okay, so not very good way to do this is so some people do this, so they say that x is in Rn, which is actually a restriction, as a little too restrictive, but it can serve as an example. Then we have, so for example, x in Rn not equal to 0. Then we have x1, x2, x1, x2, xn, right? Not equal to 0, so there exists some I such that xi not equal to 0, and then we have alpha xi equal to 0 and xi not equal to 0, so you can have, well, I guess that's totally slow, alpha xi times xi minus 1 equal to 0. 0 times xi minus 1. So xi not equal to 0, so xi minus 1 exists, and this means alpha equal to 0. Okay, and yeah, so this is a proof that gives you some intuition about what this problem is doing, but this is not fully correct because because we didn't have x in Rn. Okay, so maybe x is an infinite dimensional space, etc. Okay, and so the very careful way to do this is actually do a contradiction proof. Okay, so we start with alpha not equal to 0, then we try to derive a contradiction. Okay, so if we have alpha not equal to 0, and what we can do with this is we can find alpha of minus 1 exists. Okay, so we start with alpha x vector equal to 0, and because alpha minus 1 exists, so we multiply alpha minus 1 on both sides. Okay, so this is 0 vector. Okay, and so we have alpha minus 1 on both sides, so alpha minus 1 alpha x equal to alpha minus 1 on 0 vector. Okay, and so we are doing this very careful. So on both sides we can use the axioms. So on this side we can do the axiom to combine the scalar first. So we have 1 times x, and on the right hand side, on the right hand side here we use, okay, so here if we are very careful, then we need to prove alpha minus 1 times 0 is still 0. And so if we are very careful, then this is where we use this 0y equal to 0 thing. Okay, so this is a little tricky question. I say this for very general thing, but actually you only need this for y equal to 0. Okay, so on this side we use this alpha minus 1 times 0 times 0 vector. Okay, so we put our 0 out of the 0 vector. So 0 times anything equal to 0, so a 0 times 0 vector equals to 0. Okay, so this is where we use 0 y tilde 0 y vector equal to 0 vector. So we choose a 0 vector as a y here. Okay. And yeah, so on this side, then once again we use the scalar associative, and so we have alpha minus 1 times 0 now is scalar multiplication, so anything times 0 is 0. So now we have a 0 times 0 vector, and then we use this again once again, and we back to 0 vector. Okay. And finally we use the axiom of 1, so we have 1 times any vector equal to itself. So we have x equal to 0 vector. And this is a contradiction because we say x is not equal to 0. Okay, and yeah, so I guess in terms of this, then we are proving this in a very funny way. So if you think about scalar, then we are saying if alpha x is equal to 0 and x is not equal to 0, then we can have alpha minus 1 times alpha times x equal to 0, and then that has x equal to 0 and the contradiction. Okay, so yeah, so that's this hard question. And okay, and problem 8 is as we say, we have this is okay, 10 minutes exactly. Okay, so problem A is we are hiding something we know in a lot of notation. Okay, so the idea is we were saying that let's see if I can draw it here. So we are basically saying that if we have so we are thinking solution of Ax equal to B, right? Ax equal to B. Okay, and so we were saying that, so for Ax equal to 0, so if B equal to 0, so we are thinking about solution of Ax equal to 0, then that's like a null space of A, and it's a subspace. But when B not equal to 0, then we were saying that the solution space will be so this is the solution to A is equal to 0, and it will be like a shift of null space. Okay, so this thing is our S. Okay. It's a very like null space, but it will be like it will like what is it? Horizontal shift, not really horizontal, but a parallel shift of the null space of A. And in terms of no equation, then we can say that so everything in the solution space of A is equal to B is the homogeneous solution, and so it's like X plus, so it's a particular solution, so we have a particular solution Y here. Okay, so everything inside S can be expressed as is a particular solution Y here plus a homogeneous solution, so X in N of A. Okay, so we are thinking about this. Okay, and yeah, so everything inside S is something inside null space of A plus this particular solution shift. And okay, so as we say, if we just do standard standard vector space definition of addition and scalar multiplication, then S is not subspace because 0 might not be in S, right? Very likely A0 not in S. And so S is not subspace. You just do usual x plus x1 x2 equal to x1 plus x2. But what we can do is we can mimic the, but we know the null space is a vector space, so we can mimic the vector space addition and the scalar multiplication on S. Okay, so we'll kind of say if you have two vector adding like this, like a vector addition on null space, then we mimic it onto S. So kind of make back to null space, then do standard. So we want to add two vector in S, then we make it back to null space and do addition and make it back. Okay. And similarly, scalar multiplication, we make it back to null space and multiply and add it back. But anyway, we can do brute force verification. So if you see this, then you know that this vector addition and scalar multiplication, they have closure. But yeah, but we can do brute force check here. Okay, so if we just go by definition, so if we didn't find out that our space is just a shift of the null space, then we can do brute force verification of those two things. And brute force verification, if we go by definition, then we just need to check that when we take two elements from S, then they are still elements, and do those operations, then they are still elements of S, and so what we need to do is you need to check A is equal to B. Okay. So we want to check A of x1 and this weird scalar addition, this weird vector addition plus x2 equal to B. And yeah, and then we just go here. So this is A of, then we go. So then we want to check is equal to B, and so that's A of x1 plus x2 minus y. So now we go to HORN addition and subtraction. And then we go by linearity, then so it's very similar to the calculation we do when we think about null space. And so AX1 because x1 is inside S, so that should equal to B. Okay, and AX2 because x2 is inside this S, so that's also equal to B. So I guess that's right. So AX1 plus AX2 and minus A1 because of a linearity of matrix multiplication. And then this equal to, so AX1 equal to B, and AX2 equal to B, and AY equal to B. Yeah. And yeah, so that's equal to B as we want. And similarly, A of alpha x1. A of alpha circle x1. We don't need this one here. Alpha circle x equal to A. Let's see what's here. Alpha x minus alpha minus 1y. A of alpha x minus alpha minus 1y equal to alpha ax minus alpha minus 1ay, and that's equal to alpha minus 1 and b, because a equal to b and ay equal to b vector, and yeah, so this is 1 times b vector, that's b vector. So yeah, so we can do brute force check and to see that those two satisfy closure, meaning that you put x1, x2 inside, satisfying this a is equal to b, then this output satisfy a is equal to b, and also x1, x satisfy a is equal to b, then this alpha circle x will satisfy a x equal a alpha x equal to b. Okay, so yeah, so they satisfy closure, and we claim it's a vector space, although we only check 2 of them, but if you really want, you can check all other things, and you will find that they satisfy other ACNs of a vector space, basically because because N of A is a vector space. Okay, and yeah, so the second quadrant, then second quadrant, excuse me, yeah. Second quadrant, as we say last time, or you can see here, so we see that S is basically just a shift of this null space of A, and so the dimension of S, so here you actually need to see, you need to know this picture to know the answer, but S is a shift of null space, so S is basically the same dimension of null space, and to justify this answer, then to be careful, then you need to show quite a lot, but we are going a little easy on this. But to really justify this, then we want to find the basis of S. So if you want to be very careful, then you want to say, well, N of A is the basis, and you can find the basis of N of A. And so basis here is satisfies span and linearity. Okay. So if you are really careful, then you want to say you have a basis of N of A, and so let's say this is V1 to some V, I don't know which you call the good number, Vk, right? So some basis V1 to Vk, and then you can map to V1 plus Y, V2 plus Y, Vk plus Y. And so if you are really careful, then you say that if this is Li, then this is Li. And also you need to show that this span everything and this span everything. Okay, so span is easy to show because it's easy to see S is this whole set. Okay, so you you can show this span, this S spans, so this S span S, and this set is Li. And so you know S is a k-dimensional because it has a k-vector basis. Okay, I think we are exactly on time. So any question? Otherwise, I think that's for today. And yeah, I probably won't upload this, but if you want to check more, then we have a video, so you can look at the video version of. Yeah, you can look at the video version of this solution once again. Okay. Yeah, but PDF I'll keep it here. Okay. Okay, so see you next Monday, and we'll probably still have homework this week for 4.1.